All right, so let us start. Last time we talked about absolute stability of a Ranguta method, and in particular, we saw that for a implicit Ranguta method, and we see that by using the definition initially, right? So we say that the method is absolutely stable if the computed values or the approximated values yns are bounded when the method is applied for an initial value problem y prime is equal to lambda y, right, with initial value y naught, right? So that from that we try to see a condition, right? So basically we try to see that the absolute value of r of z, right, should be less than 1 uh, for uh, for the q's which makes the absolute value of the polynomial in z, right, which is h lambda, right? So that we call as the region for the absolute stability. So today what we are going to do is we are going to simplify that case into an explicit Ranguta method, because in explicit Ranguta method we know this, right? So in this case, right? So we know that the matrix A is a strictly lower triangular matrix. So the diagonal and the upper triangular parts are 0, right? So then when you raise it to the power s power, you get the matrix AS is equal to 0, right? So in so this implies Okay, so this is the simplification we can make when the method is explicit. So in the case of explicit Ranguta method, you know that the associated matrix A is a strictly lower triangular matrix. So when you raise it to the power s power, it will be 0. So s plus 1, s plus 2, all the powers are 0. But you know that R of Q is of this form, right? So 1 plus H B lambda transpose B transpose times lambda times I minus QA inverse E, right? So that is how we define R of Q in the original method. So in this case, you write the expansion of I minus QA, right? So then it will go all the way, right? So I plus QA squared plus QA cubed, and so all the way. But because a to the power s is 0, so the terms after QA to the power s minus 1 are all 0. So that is why I indicated that with 0, 0, 0, 0, right? So when you substitute that, you get a polynomial RQ turned out to be a polynomial in Q of degree S, right? Right, so for convenience, let us write this RQ as a rational polynomial, right? Phi of Q over psi of Q with appropriate degrees, right? So both of them can go up to maximum S degree, right? So that is just another observation which we can make, right? So now what we do is we try to prove the absolute stability, the condition for the absolute stability. So in order to get the absolute stability, you know, you have to apply the method to the initial value problem. Y prime is equal to lambda y, right? So let us go back to this original concept, right? Okay, so in this case, so this part we already know, right? So when you apply a RK method to the explicit or implicit, whatever the RK method to this initial value problem, right? So we know we have a recursive formula like this, which we proved earlier, right? So for the implicit method, it's the same for explicit method as well, right? So only difference is the formula for RQ will be different, right? So that's what we explained here, right? So the formula will be different for for explicit and implicit, but eventually this form will be same, right? So you will have a recursive formula for yn, that is yn plus 1 is equal to some polynomial in q times yn. But you all know the local truncation error is defined as the original, the real solution at Tn plus 1 minus computed solution at Tn plus 1. Whenever at the previous steps, the real value and the computed value are same. Right? So in this case, you know, this is this form. But because of the initial value problem which is given to you, you know that e to the power lambda t is the solution, right, for that differential equation. So then you apply that solution formula, right? So once you apply the solution formula, you can simplify this. Very similar kind of approach which we did for the other case, right? So that is e to the power lambda of Tn plus h minus r q of e to the power lambda Tn. And so in that case, when you do that e to the power lambda Tn, when you pull that out, you will end up with e to the power lambda h, that is e to the power q minus r of q. Okay, so again, you do the expansion for e to the power q, so you will end up with this. Let me say 1 plus q squared over 2 factorial and all the way minus rq. Right, so in this case, you know that the polynomial of rq is can go up to maximum s, right? So we see that earlier, which I just erased, right? So earlier we see that the degree of the polynomial will go up to q to the power s. So the best case scenario is you cancel all the powers up to qs. So this will be basically of order s plus 1, right? So this, right? So this is the possibility you can have, right? So this as a theorem be proved, right? So you know, right? So this is a theorem be proved, right? For the S-stage explicit method, the maximum order can be S. So the maximum, so this has to be order of S plus 1. So if this has to be order of S plus 1, then, right, so this, it should be identically at S plus 1. So then you know your RQ must be of this form. right? So only when RQ is equal to 1 plus Q squared up to QS over S factorial, right? If this happens only, right? So I can say if and only if, but you understand what I mean, right? So this will be of order of S plus 1 if and only if RQ should be exactly equal to this, right? So in this case, you have a simplified form for RQ, right? So if the order of the method, if you have the S-stage explicit Ranguta method of maximum order, right? So uh, let me write it down here. Right, so if an S-stage maximum order Ranguta method is considered, then it is absolutely stable if and only if this polynomial, absolute value of that polynomial should be less than 1 for certain Qs, right? Right, so this, for this polynomial, right, for all values of Q for which RQ is less or equal to 1, right, then the method is absolutely stable, right? For any Q that satisfies this condition, gives you the region of absolute stability. No, less or equal, right? Okay, remark. Right, so this, what we have now is, right, after doing all this theory part, right, we have a simple form for the stability polynomial, right? So absolute stability polynomial, huh? All the absolute. right? So you have a simple form for the absolute stability polynomial. This luxury is not there for you for implicit method, right? If you look at the implicit method, this stability polynomial looks very complicated, right? So you have a lot of summation inside, summation of bi, summation of ai, summation of so and so, and things like that. That is because in that case you cannot do this, because in that case this will go up to 2s plus 1, because you have a theorem which says the highest order for a implicit stage method is 2s. So then this is going to be h to the power 2s plus 1. So you are going to have lots of terms and things like that. So that is why we didn't go for that way there. But here, because it is an S stage uh, case and the maximum order can be S. So if we consider a S stage Ranguta method with maximum order, then always your polynomial RQ is going to be of this form, right? 1 plus, or basically it's the summation of q to the power s over q to the power I over I factorial, I running from 0 to s, right? So that's understandable for you. So then now it is easy, because all you need to do is to just write down the polynomial based on this. Say for example, if I have a first order polynomial, then you go up to s equal to 1. If it is a second stage, you go s equal to 2. If it is a 5 stage, you go s equal to 5. Right? So it is easy to write down the stability, absolute stability polynomial here for explicit case, right, with maximum order, so that finding the region turned out to be easier than the implicit method. Right? So that is what we are going to see in the example, right? So we are going to see how we can use this polynomial to see the boundary of the stability region, right? Right. So this is also a remark. One. Let me put it 2 here, right? Right. So that in this case, the region of absolute stability is set of all q such that r of q absolute value is less or equal to 1. So equal to 1 is obviously the boundary of the region, right? So if you want to find the region, basically you have to find the boundary, and then everything inside that boundary will be the region, right? So including the boundary. So always we try to look to find the boundary first. So basically you need to solve this RQ absolute value is equal to 1 and find all Q's such that this one is true, and that gives you the boundary of the region, and that leads to the region as well, right? So let me give you an example. Right, so two-stage Ranguta method of order 2. Right. So in this case, let us try to find the boundary and everything else. Right. So that absolute stability polynomial okay, so this RQ, right? So sorry, Q is equal to 1 plus q plus q square over 2, right? Because s is 2. So you want to get the boundary, right? So boundary of absolute stability. You solve this equation, right? So you have to solve two equations. Right? So that's very simple for you. Right? So when you get rid of this absolute value thing, you will end up with these two cases. So from this, q into q plus 2 is equal to 0, right? So q is equal to 0 comma minus 2, right? For that one, q squared plus 2q plus 4 is equal to 0. Right, so here b squared minus 4ac is negative, right? Delta A level thing, b squared is 4 minus 4ac is 16, so it's negative. So it's going to be some complex numbers, right? So it's not real part, it is complex part. So real part is enough for you to see the region, right? So okay. Right, so this is going to be the interval of absolute stability. Okay, so for this complex values, you can see the region, the whole region, right? So I just stick with the real part only, right? So between -2 and 2, right, on a real line, this method is absolutely stable, right, for all q. And then for any complex numbers whose real part falls between -2 and 0, this will be true, right? But the region on the imaginary part depends on what you have here, right? So you know that. And so that's some A level and complex analysis knowledge. You can finish this off, right? So this is fine, right? So now this case is for maximum order, right? Two stage, second order. So you are happy. You can write down the polynomial directly. RQ is equal to 1 plus q squared over 2, right? So if I say third order, third three stage, third order, then fine. You can say 1 plus q squared over 2 plus q cubed over 6, and then you can see that that should be the region, right? But there is a problem, because you know that the theorem says a stage explicit method can have a maximum of S order. So it is possible that a fifth stage method may have order 3, right? Or a third stage method may have order 2, right? So that is also a possibility, right? So in those cases, you may not choose the polynomial directly like this, right? So this is only true whenever the stage and the order are same, right? So maximum order case only you can do that, right? Otherwise, if the stage is high but the order is small, right, then you may need to go back to the original system, right? So let me start an example, and if possible I will finish it off, otherwise I will continue in the next time. And so now what I'm going to give you is a third order method, third stage method, but the order might be less. Explicit method, still explicit method, but the order can be smaller. And so let's say this. A third order method is given like this. Right, so you all clearly know it is a third stage method, right? So when I give this table, you know this, right? So everything, you know, it is a third stage method, right? These two are clear, three stage explicit, but you don't know the order, right? So they does not say anything about the order. So first thing you have to do is you have to find the order, right? If the order is 3, fine, you can directly go to the polynomial. If the order is 2, then you have to go for a different mechanism, right? So in any ways, you have to find the order. Right? First, we find the order. Right, so we have a formula structure to find the order. So we will start with summation of if right. So if this is clear, then you know it is of order 2. Sorry, order 1, right? So if summation of bj is 1, then you know at least this is of order 1, right? So you know it should be order 1. So now you have to check whether it is of order 2 or not, right? For order 2, you have to check two more things. Right, so bj, cj. So b1, c1 is 0, right? Plus b2, c2 is 2/3 times 3/3 times 3/4 plus b2 times c2, that is 0 again. So this is going to be 3 cancelled out, 1/2. This is 1/3. Okay, so you simplify that. This is 1/3. So somewhere earlier we see that and then you have to see this, right? So and then the third formula, let me write it down first. Sorry, J. So next you have to find this, right? So summation of I running from 1 to 3, right? Bi, Aij, Ci. Okay, so when I is equal to 1, when I is equal to 1, B1 is this, but C1 is 0, right? So this is basically, B1, right? Summation of A1, 1, A1, 2 plus A1, 3 into C1 plus, B2 into A2, 1 plus A2, 2 plus A2, 3 into C2 plus B3 into A3, 1 plus A3, 2 plus A3, 3 into C3, right? So this is what you will have, right? So in this case, you know that this turned out to be, right? So right, so B1, C1 is 0, so this is 0. Here B2 is this 1/4, A2 1, so it's all 2/3, and then C2 is 2/3, and then B3 is 0, so this is 0. So if we sum this, if you multiply this, you get 1/9, right? right? So this has to be 1 upon, this ended up 1 upon 9, right? But you know that it has to be 1 upon 6, right? So let's double check the work, huh? So this obviously is not 1 upon 6. So if this is 1 upon 6, then this is order 3, right? So if you look at the formula set I gave you earlier, right? If these three are fine, right? After this, if this one is 1 upon 6, then we say that the method is order 3. But unfortunately, this one is 1 upon 9, so not 1 upon 6. So only this can be order 2. Right, so this is of order 2. Right, so now there's a problem, right? So you know this is order 2, but state 3. So you cannot apply the polynomial directly. So what you have to do is you have to write down the polynomial, right, from the regular form. Right, so now we have another form for the polynomial, right? Let's say B transpose right? If you remember, this is an alternative way of writing the polynomial which we write earlier as well, right? By using the expansion of 1 minus QA inverse, right? The binomial kind of expansion for 1 minus QA inverse, we get a formula like this, right? So you can write down this terms, right? So these terms, right? One obviously you know, so you have to find B transpose E, right? So you know E is all ones, right? So B transpose E. So let me write down 1 and then you can find it out, find the rest, right? B transpose is this, right? So I have this 3/4 0, right? E is 1 1 1, right? So if you do this, you know you get 1, right? And then you find the others, right? B transpose AE. A is 0 0 0. What do you have? 2/3 0 0 0 2/3 0. E is this 1 1 1. So you multiply all of them, row into column, row into column, row into column. So this is 3 3 3 cancel, 2 cancel, 1/2, this into this 0, this into this 0 times 1 1 1. It's going to be 1/2. Okay, right? So then you find B transpose A squared. Okay, so you find B transpose A squared. So I already have B transpose A, right? So let me write it down. A again, right? So this you all know, this is B transpose A times C, right? So I already have B transpose A multiplied here so that it is easy for me to use it. And then A is 0 0 0, 2/3 0 0, 0, 2/3, 0, and then 1, 1, 1. So this into this is 0, this into that is 0, this into that is 0, times 1, 1, 1. So this is going to be 0. Okay? So what you can do is, you get, so your R of Q is 1 plus B transpose E is 1. So that is Q plus half Q squared. And then the rest is 0. Right? So you all know if B transpose A squared is 0, then B transpose A cubed is 0, and all those are 0. So you don't need to worry about the rest. So this is your polynomial. So you can find the other things from this in a similar way, right? So similar kind of polynomial earlier also we have, so we can do that, right? So we will stop here and then continue with another example on Monday, and we will talk a little bit more about other types of stability as well, right? So we will do it on Monday class.